Assalamualaikum and good day, everyone. My name is Sada Hakimi Ben Shano Aizam, and today me and my team will be presenting our project titled Autonomous Dual Payload Development System. So, this project focuses on designing, integrating, and validating lightweight payload deployment mechanism for unmanned aerial vehicle or UAVs. The objective is to allow the drone to autonomously release two payloads at different targets and the location while maintaining stable flight and ensuring the safety of the onboard electronics. So, page 2. So the main objective of this project is to develop a robust, lightweight electromechanical payload release mechanism that can be integrated into existing UAVs without compromising its flight performance or electrical reliability. Our design is based on three major engineering constraints, which is the first one, mechanical constraint. The total additional payload mechanism remains below 200 grams. Keeping the weight low ensures the drone maintains sufficient flight endurance and that its center of gravity remains balanced. The second one is electrical constraint, which is high current actuators such as servos can introduce voltage drops or electrical noise, which may affect sensitive avionics like the flight controller. Therefore, our design involves the power supply to actuators from the flight control electronics. And finally, it's the operational constraints. The system must be capable of autonomously releasing two payloads independent at predetermined GPS coordinates. So the next slide is system architecture isolating data from power for power. This slide illustrates the overall system architecture. One of our important design principles is the complete separation of data flow and power flow. At the top, we can see the data flow. The ground control station communicates with Pixhawk flight controller through telemetry with the Mavlink protocol based on the mission plan. The Pixhawk sends PWM signals to the servo, which controls the payload release mechanism. At the bottom, we can see the power flow. The LiPo battery supplies power to an external battery elimination circuit or BEC, which regulates the voltage to 5 volts before flight. This means the servos receive their power independently from flight controllers to prevent interference and noise, like I said earlier. By isolating the high current actuators, we improve the reliability and safety of the UAV, so not to cause accidents.
So, hi, my name is Muhammad Faris Iskandar. So, moving on to the mechanical design. So, the primary challenge is converting the rotational output of the servo used in this system into a clean linear latch displacement. So, we couldn't just think where to put the latch and where to put the servo because it's all on the matter of the COG, the center of gravity itself. So, to handle this, we selected the Corona DS939 MG actuator, which is a much more professional and much more industrial use servo in the market right now. So we chose this specific model for two reasons. Its full metal gear set and also the highest torque of 2.7 kg/cm that prevents the gear from stripping over time under the continuous passive strain of the spring while the system is locked. So if you can see at the cat model on the left and also the right, you can see the compact dual latch arrangement designed to keep the mechanical footprint minimal while also maximizing structural rigidity during high vibrational flight phases. So moving on to the page number 5, next page. So we will talk about the passive security and also the mass budget optimization. So when we talk about this, safety and weights are always at war in UAV design. So when we see about this part, we engineered a passive security system. As you can see in the diagram, even if the drone suffers a complete mid-flight power blackout, meaning that it doesn't have any power mid-flight, a worst case scenario, the continuous passive string tension guarantees that the latch remains completely locked. So it means that the F spring, the spring force, keeps the hook engaged. So for the mass budget, so for this project, we actually follows the requirement. We allocate around 200 grams. So we had a strict constraint of keeping the entire mechanism under 200 grams, but optimizing the 3D printed using PLA and also using plastic to 3D print the whole items and also the whole project itself, we can bring it down, the main chassis down to 82 grams, utilizing lightweight servos at 25 grams total, and keeping the latch hardware to 59.5 grams. So our total dry mass come out at 166.5 gram. Next. So enough talk about the mechanical. We actually want to go more further into the electrical part. So, servos are notorious for drawing dangerous peak currents. As you know that servos is actually using a lot of current, especially in microcontrollers nowadays. So, this current spike can drop the voltage enough to cause a catastrophic avionics brownout. So, meaning that there is a problem during the flight. So, we actually want to solve this and actually want to eliminate this risk by isolating the data and power path. As you can see in the schematic, the PixHawk only sends the PWM data signals via the out port, specifically configured via parameters servo 9 and also servo 10. The high current power, however, is routed from the LiPo battery through a 3 ampere external BEC, which regulates it safely to 5 volt or 6 volt. So we also added another safety where we added a 220 microfarad decoupling capacitor. So it eliminates the voltage ripples. Enough said about the electrical. We want to go more on the SITL. So I pass the baton to Hafiz. So
Okay, so now for autonomous mission logic part. So basically what we have to do that we have like different waypoints. First of all, we start off with takeoff and also end with return to launch. So the way we actually configuring the uh, movement is actually first, of course, we take off from the land up above to the 10-meter altitude, and then it start moving to the waypoint A. So it move in way of it being inclining from the ground, actually 10 meter to the waypoint A. So when it reach, it will just stay at the 10 meters suggested by the image. And next, as per request on the waypoint B, which is our first drop point, we make it drop into the waypoint by gradually, not by moving very vertical way. So the way we do, actually we have 3 different functions to trigger servo and to same waypoint at the drop point. I'll explain later on the simulation part. So that's how we actually move the robot as suggested by the slide. So it move incline and then stay at the point until it close to the waypoint B, and then start to decline gradually to the point B at 5-meter altitude. So it climb back to 10 meter for waypoint C, and then drop back to waypoint 5-meter waypoint D, and then it in, in, incline gradually again up up until it reach 10 meter and then return to launch. So that's how we make it. So next I will show you how it gonna look on the mission planner. So as you can see on the mission planner here, so we actually have 15 function. So the way we actually tackling this is there's 3 special function just for the servo trigger. So first of all, of course, take off, and then we move to waypoint A. Suggested here, this is a takeoff point, and we'll move to waypoint A, the blue one here, the green one here, and then next to the first drop point, which is point B. So the way we did setting is up is just by changing the altitude on this column here. So here we can actually change the altitude to 10 meter, 5 meter, and so on and so forth. So the 3 different function that we actually use is actually first set servo. Basically, we want the servo actually move like the servo arm actually move like this. So first we need to set the servo change into the 1500 RPM. Basically, just turn it up to 90 degree, and then 1900 PWM. So it just like move 90 degree, and then we make it delay 1 second to give like a resting time and not instantly for the payload to actually drop. So and then after the 1 second delay, we close up the servo arm again. So that's why we need 2 different servo command, servo function on the drop point. So next we actually create another one wire point on the same drop point to actually increase its raise its like altitude vertically before it start moving again to the next waypoint. Since it is just to emulate the smoothness of the delivery robot. So yeah, it like raise up vertically before start moving. We actually add 5-second delay to for it to actually raise up to the 10 meter altitude again and not like moving gradually. So actually we can emulate on how the robot move. Like we can make it like drop like gradually downward or gradually upward. Yeah, so we can also make it like vertically move or vertically move downward. So there's 2 way on approaching this. So we just show that we can do both way. So that's how it is. And then we move to the next waypoint and then repeat the same thing on the waypoint D, and then next waypoint, and then to the return to launch. So that's how we set up the mission planner. I will include the simulation video at the end of the video. So yeah. So next is actually checking up the data. So basically we have 2 different data here. First is actually altitude trace for road pitch and yaw. This is actually like very zoom out image, and the 3 different altitude form is actually very variable. Like it's very unstable. Like when you actually climbing the incline, it can like roll around. Actually it tries to control to get the stabilize, but it's not gonna be like 100% smooth. There's a need a lot of tuning needed to actually achieve that, and I believe in payload system there's no extreme necessary, since it's just a package, a very light package, and our payload system actually very secure, so we don't need like a control on that unless it's like a hook or something. And if a hook, then we need to be cautious of that lah. So next with altitude, it just raise up to 10, down to 5, and so on and so forth. And finally, this is just servo output and also battery spike. So as you can see that battery spike during servo as we actually triggered multiple stuff, and this is just like motor and motor function and stuff. So that's all of my part. Thank you.